Okay. Right.
For the stalwarts who have shown up, thank you. This is the middle of the summer meeting of Gemquest, and we're doing a first. And so those who have come will experience something that no one else has experienced on Gemquest before. And that is two separate subjects by two separate speakers. We've had up to four speakers on one subject in the past, but never diverged as we're doing today. And we're having a talk about one gem that happens to be organic and another that's igneous. So I think we're looking at two opposite ends of the geological spectrum in a way, in terms of the sources for the gems we're talking about. And the gems we're talking about tonight or today, depending where you are jet and sunstone, and both stones. Well, I must admit, I don't have a sample of jet in my gem collection, but I certainly do have some sunstone. So I'm very keenly interested to learn what we're going to learn today. The first present, we're going to do it one and then the other. The first speaker will be a very interesting lady, Sarah Steele, who is working towards her PhD in subjects that are beyond me. Um, she has her FGA and her DGA, and she not only is all of that, but she happens to run a jet lapidary in Whitby, the home of British Jet. And the business she runs cuts in excess of 40,000 stones annually. And she's also curator of jet at the Whitby Museum, making her the most knowledgeable person in the world about jet. I think we can safely say that. Her degree in geology has led her into weird and wonderful places. And she did that 5 years ago. And now she's in the final stages of finishing her PhD in archaeogemology of jet, and also jetonization models. I don't know, that doesn't sound like it's going to be jet propelled, but anyway, country of origin determination and material cultural of jets globally, which is a very ambitious goal, I would say. So we have a very a lovely lady, Sarah Steele, will share with us about vampires, mummies, demonic possession, and the legacy of Whitby Jet. And thank you so much, first of all, before we start, to Clemens for making this happen, and for all of you for coming, and especially this moment to Sarah for taking the time and effort to present to us today.
Okay, are we ready?
Absolutely.
So yeah, thank you for inviting me, first of all. I don't get many opportunities to speak about black organic gemstones, so here we go. And I did promise Ray that there would be at least one slide on Queen Victoria, so here it is especially for Ray. And of course, most people think about jet from a 19th century perspective, and the jewellery on the left really is what we tend to think of when we think of this material. And Queen Victoria, really, on the death of Albert in 1861, adopted Victorian full mourning etiquette for the rest of her life. So we always think of Victoria in association with jet, but the real jet boom started with the death of George IV in 1830. And at that time, there's actually a Lord Chamberlain's office issues a decree, and they say that the entire British Empire is in mourning, and that's a quarter of the entire world's population. And they stipulate that the ornament, the jewelry should be jets. So at that time period, that means one thing, it means Whitby Jet. So really, at that time, Whitby is a town that's founded on death, let's say. But what is jet? So jet was first defined geologically by Stack in 1928 as being formed from drifted wood with a secondary impregnation of bitumen from the surrounding sedimentary environment. And with minor geological modification, that seems a sensible proposal for the jets in the Whitby area of North Yorkshire. However, there's absolutely no geological or gemological consensus as to what jet is or how wood is jetonized. There are two other models proposed, and the first one is Kulital. They're studying a submerged forest in Peru, and they noticed that when waterlogged wood that's essentially been in an anaerobic environment is re-exposed to oxygen and, crucially, sunlight, they could see chemical changes in that wood. And they therefore suggested that jetonization was actually a rapid form of mummification. And it requires nothing in the way of geological time, so it happens immediately upon deposition. And they suggest that the jets of Whitby are also formed by this model. There's a third model that's proposed. This is Travers and Colvard. They are working in Jet Basin in Utah in the 1960s. Huge jet reserve. We know jet mined from Utah was sent back to Whitby to fulfill the demand for Victorian jet during the 19th century. And they actually propose a species dependent model. They said that what they observe is certain wood species are resinous. If these woods are preserved and for some reason those resins are retained within the lignin framework of the wood, and that resin doesn't escape post sedimentary process, it goes on to modify the reaction medium in which the coalification takes place. So these two later models argue that irrelevant of how the jet is formed, it is chemically and structurally identical to the jets that we see in Europe. So it's very rare, unusual from if it's certainly in the mineral world that we can have materials with exactly the same properties formed in different geological time periods and different geological contexts, essentially. But that's what we seem to have at the minute. I would, however, argue that not all jet was created equally. So in the Whitby stratigraphy, we have four very distinct varieties of jets. So these jets look very different morphologically, and therefore probably structurally and chemically are different entities. So how do these materials fit into the proposed models for jets? Well, what we've allowed, certainly in the UK, is we've allowed archaeologists to define what this geological material jet is, because the geologists really haven't been particularly interested in it. And archaeology is very much a forensic approach. So finds are excavated. In the image there, we've got some early Bronze Age jet artifacts. And the archaeologists have looked at these artifacts, assumed historically that these are jets, and they've defined the properties of jet retrospectively from curated and excavated finds. They may consult Pliny the Elder and the Venerable Bede, but invariably the jet's going to end up in a drawer because black organic opaque gems scare gemologists and they equally scare archaeologists. And really, archaeologists have believed that it's absolutely not possible to visually distinguish between certain gem quality hydrocarbons. So we see a quote there: jet will be used to cover jets, lignites, coals, shales, even in cases when the raw materials have been confirmed analytically. So we see even archaeologists have very much used jet, the three-letter word jet, as a placeholder for uncertainty. They're using it as a generic term to cover lots of different geological materials. Now, in the 1980s, coal petrologists did get involved with archaeologists, but of course they're economic geologists and they're concerned with fuel performance. So they tend to look at things like ash yield, oil generation potential, coking parameters, and thermal maturities of coals, because that tends to define how many calories we're going to get off when we burn coal. So when jet is looked at from that perspective, it was assumed that jet was a lignite. Now, a lignite is actually the lowest metamorphic grade of coal. But that term lignite or brown coal has then filtered into our gemological databases, our lexicon of gemological information on jet. So GEMA here are saying that it's a form of brown coal or lignite. Now, I have spent many, many hours at the National History Museum in London, at the Scottish Shale Museum, at the Hunterian in Scotland, looking at coals. And really, my approach is very much as a lapidary practitioner approach. I don't really care what the coal is labeled as. What I'm looking at is, can I polish this material? And I can make a silk purse from a sow's ear, but I can guarantee from a lapidary perspective, I would struggle with the material on the left. And that is a good quality peat derived lignite. So I think anybody looking at that would agree that that material shares few of the gemological properties with the jet on the right. And yet it's curious that nobody has ever questioned why, if jet's a lignite, does it not look like a lignite? So how would gemologists perhaps have addressed this problem? Well, again, unfortunately, gemology is very much a forensic approach. We're given a cut stone quite often. We'll run a set of tests looking at optical properties within this. And then we're going to look up the answers, the data we receive from those tests. We're going to look those up in a database and we're going to assign identity, species identity to the best of our abilities. But when I look as a gemologist and also look as a jet practitioner at the values that are published for jets, I do not recognize any of the values in our notes as values I have seen in the last 40 years working this material commercially. And the problems exist even in things like color and luster and hardness. What I see are values that, to my eye, are completely nonsensical from a jet perspective. So we have a problem. And as early as 1934, Russian coal petrologist Kushnikov noted it's difficult to find another material associated with so many vague and false concepts as jets. Even the definitions in the dictionaries are different and contradictory. And he also notes that this material on the left there, I took this picture at Tucson this year. That's the primary material that is sold as jet today, certainly in the US. $45 a kilogram. That is actually a Siberian sapropelic coal. And he says that although this material is sold as jet, it bears nothing in common with the jets known from Europe that have been used for millennia as a culturally important material. So this is not new knowledge. And yet the gem trade sells this material as jet because in Russian it's known as gagat. And in Latin, jet is gagate, and the only word in English that gagat translates to is jet. So we have no other language to actually translate these Russian materials. And in Russia, they actually identify 11 different species, varieties of jet, whereas in Britain, we just call it all jet. Now, what's going on here? So GIA wrote an article in 1996 saying that black stone identification was acknowledged to be the most challenging area of 21st century gemology. And it very much is, because as gemologists, we're always in search of this elusive spectrum. Now, it's really interesting that in 1897, following a short holiday to Whitby, Bram Stoker is inspired to write the greatest Gothic novel of all time, Dracula. Now, he uses Dracula. In Dracula, he uses the language of stones to give a sense of materiality of place. And he tells us that deep below our feet in Whitby, there is a material that was once alive that's now preserved for all eternity in death. Jet is eerily in a vampiric state. And we all know that Stoker's brand of vampire gives no reflection. He gives no visual spectrum in a mirror that we can see in the visual 400 to 700 nanometers. And exactly the same way, jet gives no visible spectrum in the visible field. It essentially is an energy vampire. All of the wavelengths of light that fall on the surface of jet are actually bonded with it within the electrons in the jet. We don't see anything. And that absorption actually goes way into the infrared and ultraviolet from jet. So it makes it incredibly difficult to get a good spectrum using any wavelength of energy. Now, saying that, generic spectra have been published for jets, and the authors of these papers claim that they can identify species and quite often geographical locality using these spectra. Now, if we look at looking at the vibrational bonds, so FTIR on the right there, although that is perhaps a typical spectra for gem quality jets, when I've looked at my sample suites, true jet from anywhere on the planet gives an identical spectra. And I'm actually seeing we have more variety in the spectra between the 4 varieties of jet in Whitby than we have between jet from Spain, jet from Turkey, jet from the US. So that's quite unusual. So we can't definitively say that just because we have certain peaks missing that that material isn't a true jet. On the left there, pyrolysis GC mass spectra, again claiming to be a generic spectra from jets from Yorkshire. When we look at mass spectroscopy, on jets as well. We're seeing that there is variety, but there's also variety each locality. And it's also very difficult if we look at archaeological artifacts to fit them into any of the jet spectra, even if we know that artifact is from a very specific locality. And really, that's the problem with bulk chemistry type approaches to very pure hydrocarbons. Jet has almost 90% carbon and really high hydrogen levels, maybe 9% hydrogen. All the other all the only other things we have in there essentially is oxygen and a bit of sulfur and nitrogen. So that's the same also with some of the other coal materials that are used for jewelry purposes. So really just bulk chemistry isn't showing us the full picture. Now, when I first started my PhD and I sat down with my supervisory team and explained to them I wanted to approach this, yes, from a lapidary practitioner perspective, but really from an archaeogemology perspective. So archaeogemology, as defined by Cheetham Lule, really is we want to establish gem species non-destructively and also country of origin. And I explained to them how gemologists identify stones and the problems with black stones. They said to me, well, that sounds, Sarah, like you're trying to milk a cow in the dark. And that very much is really describes what we're trying to do with black stones. But luckily, we do have some tried and tested methods available to us. These are suggested by GEMA and GIA as methods we can use to identify jets. And I like to call these ye old quaint gemological testing methods. And my particular favourite is burn it with thy bodkin. Now, if you don't know what a bodkin is, it's the metal needle on the screen there. They're about 6 inches long, and you have an ear scoop on one end. So you'll get some earwax, and then you'll get some piece of ribbon and you will smear the end with earwax so that you can thread it through the eye of that needle. And then your servant would lace your sleeves to your bodice or join your bodice to your skirt. This gemological testing method predates the zip by a number of centuries, and it operates very much like a witch trial. So you heat your needle up and you plunge it into your jet jewelry. And if it burned, oh dear, it was jet, we've destroyed it. And if it didn't burn, then it was a stone. So in the same way, if we're going to swim a witch, we're going to try and drown the witch. If it is a witch, it's going to float and we'll take it out of the water and burn it. If it isn't, it drowned. Oh dear, we killed it. So GIA calls this the thermal reaction test. Let's not beat about the bush. This is trial by fire, and we're still suggesting that we do this. Now, I would argue that we need to ban the bodkin test because it is a medieval technique, and probably I would question the sanity of the person that invented it, even in the medieval period. If we need to set fire to a gem to appraise it, we're probably in the wrong job. All burning coals smell, guess what, like burning coal. Easiest way to devalue our gemstone is to set fire to it. But more importantly, if you're so unfamiliar with the material that you are questioning those three brooches in the image there. One of them is jet, one of them is dyed pressed cow's horn, but the other one is celluloid. And celluloid is sometimes referred to as nitrocellulose. It's the primary ingredient of modern day gunpowder. If we put a hot needle in that, we're going to have a very small incendiary explosion. So, I've suggested to both GIA and GEMA, they're not probably insured to suggest that students try this method. It's great fun, don't get me wrong, but you may lose a finger. Now, we have a slightly second less destructive, dangerous test. This one is doth it draw to it chaff. For those who do not speak Middle English, I will translate this as can we induce a triboelectric charge? So what we have to do is go to a field. We need to gather some wheat or corn, separate the wheat from the chaff. Then we have to charge the jet jewelry by rubbing it incredibly vigorously on a woolen tunic. We then offer the jet to the chaff, and if it attracts it to it, then the chances are it is jets, because jet is highly triboelectric. Now, this was a good test in the medieval period, and my colleagues in Spain still advocate for this test. Unfortunately, almost all the Victorian semi-synthetic biopolymers that they invented in a quest to make a material that looked and felt like jet are highly triboelectric. So things like vulcanite is going to demonstrate this property. Now, there are two other medieval tests that are not actually documented in the Gem notes, and the reason why will become apparent. The first one, will it kill a wanton woman? So this one, we have to take a woman, we have to get her naked, we put her in a bath, we put some jet dust in there. If she is a virgin, she's going to sit there completely innocent, not aware of her naked body. If she isn't a virgin, she's going to stand up and will immediately die from shame. So yes, this potentially, according to the Pliny the Elder, will we can use this as a jet test, but we're going to kill a woman. So it's not ideal. We do have a fourth test. This is in an occult lapidary, 14th century British lapidary. And we're told that a man exposed to jet fumes, and really for the first 1,000 years of jet's use, all authors talk about burning it for banishing, for exorcism, not for jewelry purposes. But we're told if jet fumes are wafted over a man, he's going to be knocked to the ground. He will be stained with his own foam. I don't even want to think what that means. He's going to wallow in all directions. And then we're also told that the horned goddess delights in her heart when she sees men subjected to this sort of challenge. So again, if anybody wants to try this, I'm looking for a victim. So I'm sure most of you are thinking, well, why doesn't she just send the whole sample suite to a lab and zap it? Well, as I mentioned earlier, with looking for a spectrum, you're only as good as your database, and there are no gem laboratories on Earth that have the databases that we need for precious hydrocarbons, so precious coals, gem quality hydrocarbons. So I've spent the last 25 years assembling my data sample suite before I've even started my PhD. Now, it's very difficult to collect samples on the beaches. So jet today, legally, we're not allowed to mine it. We have to collect material that's washed in on the tide. The problem is we have many, many hydrocarbon species on our beaches. And historically, I would criticize the papers that have been published because often they're using sea-washed material as a generic piece of Whitby jet. Not only do we not know that the jet came from the Whitby stratigraphy, but we actually don't know what variety they're using. Likewise, when specimens are acquired from museum collections, and I'm sure Robin Hanson will mind me saying, certainly the jet at the Natural History Museum, there is many, many misidentified materials in the collections there that are labelled as jets. I can see they're not jets, but if academics are given those materials to sample, they go on to add to the nonsense that's been published on jet. So luckily in North Yorkshire, we have 300 documented jet mines. We didn't believe any of them were large-scale mines until recently. So in 2016, we discovered a mine that's 8 kilometers long. So I'm able to access these mines. They're completely unpropped. Nobody's been in them for 150 years, and they are, up to 4 miles in length. So I'm able to go in there with cavers. I wouldn't dare go in there alone, but it gives me an opportunity to study jet in the host rock. Because if I can't see it in the host stratigraphy, I can't propose methods to explain not only the jetonization of wood in the Yorkshire area, but also, what's controlling gem quality, what's controlling the varieties we're seeing. So I'm able to look at it in the host rock. And only by doing that can I answer really important questions which I did not expect to be answering in my thesis, such as what colour is jet? Now, I've known since I was 7 that jet is jet black. The term jet black is reserved in the English-speaking world for the epitome of blackness. It's coined by William Shakespeare in Henry VI, Part 2, Act 2, Scene 1, and we have black, forsooth, coal black as jet. He did not say blackish brown or brown forsooth. He said black. All the writers from antiquity, Pliny the Elder, the Venerable Bede, Solinus, Dioscordes, everybody that's written on jet has said it's black. And yet within our gemological notes, we're told it can be black or brown. So here we have 2 Roman bangles, both described as jet by the archaeology company, that trust that actually owns these. Now, immediately I'm questioning the identification of the brown bangle. Now, there is somewhere on Earth where the colours of jet get even more random, and that's Turkey. Stamped there from Turkey. Turkey are one of only two nations that have featured their national stone on a stamp, the other one being Spain. I'm still waiting for the British stamp with jet on it. But we know that Jet is a historical, Turkey is a historical locality for Jet. Pliny references Jet from Lycia, which today is in modern day Turkey. But he also tells us that in Lukola, where the red highlighted area with the randomly Father Christmas on it, that Jet washes up there over an area of 12 stadia, which I believe is about 12 and a half miles. No, sorry, 2.5 miles. He also gives us a good geological description of jet. He tells us, thankfully, that it's black, it's smooth, light porous, differs little from wood in appearance, is brittle, emits a disagreeable odour, and marks on pottery can't be effaced. And when it's burnt, it gives off a sulphurous smell. But there is, oh, I forgot to put this slide in. This is actually the first image, the first illustration of any mineral, I'm going to call it mineral, on Earth is actually an image of jet, believe it or not. This was actually illustrated in Constantinople in 512, there or thereabouts, and it's actually in the Vienna Codex, and it's a text by Dioscorides, so a first century text, and there is an appendix on Stings and Bites by Nicander, which was written in the 2nd century BC. And he's saying that you powder jet and you mix it with the marrow of stag to treat snake bite. So that's actually a Turkish text. So the first ever mineral was jet that was illustrated. But there are a number of problems with Turkey. A few years ago, I was asked to be a keynote speaker at the Turkish Geological Symposium. So I read all the literature that had been written on the Turkish material Altu Taşır. Now, Altu Taşır is this material that the Turkish refer to as black amber, and it's also referred to as jet. Now, strangely, and there is no other analogy, certainly in the English-speaking world, where geologists do not accept that amber is the resin of a tree. So in Turkey, and there are many, many academics, both faculty members from universities and engineering geologists, that say that black amber or Altu Taşır is resin-rich woods that have been compressed. So they have a wood element to them. So we're also told that in Turkey, this Altu Taşır, the jet, occurs with lignite. But we're told it comes in black, velvet black, brown, grey, and green. And more worryingly, when I read this, it said the most interesting characteristics of Altu Taşır is that its softness when first excavated. It comes out of the ground soft and only begins to harden when exposed to the air. So when I read this, I panicked that Whitby jet is soft if I dug far enough into a cliff. But more likely, I actually wondered whether Altu Taşır wasn't jet and perhaps it's a pyrobitumen or an asphalt material, not a true jet. So the only way to answer this was to go to the far northeast of Turkey on a field trip. It's a military controlled zone, so I can't go without government clearance. And the Turkish government wouldn't give me permission to go unless I was with Ministry of Mining and Engineering geologists. So Dr. Cheetham Lule, who I'm sure many of you know, was able to facilitate that visit. So we went a couple of years ago to the Altu district. And the Altu Taşır, the jet there is mined above 2,200 meters in the Dutlu Mountains. And the Turkish government say there are 110 active jet mines operational in Turkey today. So it was one place on Earth where I could go and actually work with artisanal miners. And it's very much a small scale operation. So in this mine, two brothers are operating the mine. The mines are unpropped. They use jackhammers, but no explosives. So very much from a mining geology perspective, the Turkish mines are very similar to the Whitby mines, much less mud, which was very nice. It was interesting. So when we go in the mines, obviously in the UK, we used to have in hard hats, lighting, sort of underground location devices so that we don't get lost. That's not the case in Turkey. So when we said to the miner, shouldn't we be wearing hard hats? He said, if Allah wishes you to come out of my mine alive, then you will come out alive. At that point, the other geologists decided that I could take one for the team and go to the working face of the mine. So I followed the miner to the end of the passage and was rewarded by the most jet I've ever seen in the host stratigraphy. Managed to take this picture. And why this is significant is here we have two varieties of jet in incredibly close depositional context. So I'm going to go so far as to say that this wood was probably deposited on the same day. But at the bottom there we have hard Turkish jet, and above it we have brittle working Turkish jet. So the theory is that certainly in the UK is that hard jet is formed in a marine environment and brittle jets are formed in fresh water. So I had suspected from what I've seen in the Yorkshire mines that this is not the case. But here in Turkey, not only am I seeing two varieties, I'm seeing them in the same depositional facies, which is really important. Um, Obviously, we had government geologists with us, and the miners took us to the best sites, the most productive mines with the best quality gem material. When I showed them images of other Whitby jet varieties and said, have you ever seen materials like this? They immediately said, yes, yes, we have, and took us to those localities. So on the left there, we have cord jet. So that's a variety we also have in Whitby. So essentially, we have mineralized wood, so petrified woods with a jetonized skin on the outside. Very common in the Whitby area, very common in Turkey. I've also seen it in the mines in France and the mines in Spain. On the right there, we've got a mineralized, peri-mineralized jet. So there's a very high clay content in that wood. It's been impregnated with clay and sediment during the preservation process. We also have a variety of jet in Turkey, which I believe is absolutely unique to Turkey. I've not seen this anywhere else in the world. And we seem to have jetonization and mineralization happening at the same time. So we've got jetonized cores, we've got petrified cores, both preserving the wood texture. So this is a pretty unique. And again, it gives us a whole different story about how wood is jetonized if we can have it mineralized and jetonized in the same context. Even more exciting than the 110 mines were the fact that in the town of Altu, there is an entire shopping mall dedicated to jet shops. So it was my dream place, really. And in these shopping malls, I was able to speak to the manufacturers, the lapidaries that work the material. And I found that if I go with my academic hat on and say, I'm a researcher, can you give me specimens of jet for analysis or can you tell me about it? The lapidaries really have walls up, and I admit I'm the same. I get many, many requests every year to my business asking for samples of jet for academic study. And I am very reluctant to give them those because they don't understand what they're asking for, because this is a whole family of gem materials. It's like asking for a generic garnet. So if I give them one specimen, what variety of jet would they like? Are they going to look at all the varieties? And historically, that hasn't happened. But if I go to a jet manufacturing locality and I say, I'm a jet worker, can we sit together and cut some stones? People are really keen to do that. So this lady agreed that we could cut some stones. She would cut some Whitby jet that I'd taken with her, but she actually wanted to test me first. So I had to make a brooch. And she announced that I did show some potential as a lapidary, which I was slightly relieved, having worked it commercially for 40 years. And then she did agree to cut some Whitby jet. And this lady has worked jet commercially since she was 7. She's not had much in the way of education. She certainly isn't a chemist. But the minute she started cutting the jet, she said, right, I can feel the texture slightly different. It's slightly more plasticky on the diamond when we're cutting it. She said, I can smell there is a oil content to your jet. She said, but whereas the Turkish jet smells like petrol, yours smells like diesel. You've got a different oil in there. She also said, I can smell sulfur, but I can't smell the metallic tang that would indicate this is pyrite. So I would suggest that your sulfur isn't able to make pyrites. There is no chemist that has ever looked at jets that has been able to give that sort of nuanced description of jets. And this is why really the practitioner approach is so important for gem identification and country of origin testing, because jet workers around the world are using other factors. We're using sound, we're using smell, and we're using touch. Yes, we use a visual technique, but where we can't see anything in the visual realm, we're using our other senses. So if we cut jets, we can identify our own indigenous materials through smell. But it's very difficult to do that, obviously, in the lab. And what did I learn in Turkey? Well, the first and most important thing is never go anywhere without a hair bubble. Obviously, that was important. It took me ages to get that dust and dirt out of my hair. Secondly, I learned that jet is black. Everybody we worked with in Turkey, Cheatham asked the question, what colour is Altu Tasha? And they also, all of them said, well, it's black, obviously. And one of them even said, if I was the world expert, why on earth did I not know what colour jet was? But when I asked them, why then in your websites, in your point of sale literature, are you saying it can be black, brown, green, or grey? They said, well, that's what the academics say. So the academics simply have not done due diligence because we rely on peer-reviewed papers and we cannot make a claim. So I cannot make a claim in my thesis that jet is black unless I prove it, because every other author on the subject has said it can be brown, green, or grey. And it's incredibly difficult to prove that a material is black because I'm proving absence of colour. Secondly, I found that jet is not soft. So again, here we have a problem with language. So some of you maybe have read Broken Bangle, the amazing book on jade and jadeite. And in that, there's a whole chapter on how the terms hard and jet, soft jade came into being from a gemological perspective. And it was an error in translation from the Chinese. So the academics that have published on this soft Turkish jet have published in English, and they've used language which really would have been appropriate for pottery and clay production. So when we asked the miner, is the material soft? Do you mold it and then it hardens on exposure to the air? He said yes. When we asked him to show us the soft jet, he gave us fully lithified material. I did notice, however, he was keeping it underwater. So when Cheatham re-asked the question in terminology he would understand if he was a potter, he said, no, no, of course not. It's a lapidary term, hard jet and soft jet. And we in Whitby have hard jet and soft jet, but it doesn't refer to hardness. It refers to stability. And, you know, when geologists, gemologists haven't understood that lapidary terminology can be very different to, the lay person's understanding, these mistakes happen. So in this case, it was an error in language. You know, what is written in one language doesn't translate well into English. So all jet is hard. But what I really learned is I'll follow a man that doesn't speak a word of English down a very dark hole for a very, very long way on my hands and knees if he promises this jet at the end of the tunnel. And I don't know really what that says about me. But that was the main thing I learnt. You will, however, be pleased to know I have zapped it with lots of wavelengths of energy. So proton emission X-ray and gamma spectroscopy. We've obviously used SEM. We've had samples at the Hadron Collider at CERN. I've looked at I've looked at infrared models. I've looked at XRF. I've looked at pyrolysis GC mass spec. And really the main significant breakthrough we've made, and essentially my initial sampling was done with my research colleague, Dr. Richard Hark at the University of Yale. We are pretty confident we can distinguish between Whitby jet and Spanish jet using stable isotope analysis. And really, from a Roman perspective onwards, that's the holy grail for archaeology to be able to differentiate between those two country of origins. So we think we are looking at the climatic conditions when the wood was deposited. Of course, we could be looking at climate when the wood grew. So we think it's depositional. We're hoping to publish on that very soon. But the real drive for me, yes, I want to answer those questions in the archaeological record, but I want to protect the indigenous groups of jet lapidaries today. And there are only 6 groups of us left on the planet today. We've lost the French industry, the Portuguese industry, and the German industry. They're unlikely to come back. But we do have 6 groups that still work jet today. In Whitby, we're down to 7 manufacturers. If we were elephants, we would be essentially extinct. The same in Spain. All of us are threatened by the retail of these Russian and Chinese materials, which are sold unpoliced as true jets. So we desperately need trading standards authorities to be able to differentiate, and then we can legally protect our indigenous materials. So I've given you witches, I've given you vampires, I've given you mummies. I'm now going to give you Frankenstein's monster. In 2021, the Seattle Times published this article, Discovery of a New Gemstone Turns Japan Coal into Gold. What they'd done in a commercial gold mine, they had hit a seam of coal, probably a cannel coal or a boghead coal that is not economically viable. But these coals are good lapidary materials. And what they've done is powdered it and then bizarrely melted amber and mixed the two together. So they claim they have taken the natural material and they've improved on colour and luster and stability. They haven't done that, of course. They've created Frankenstein's monster. But the reason the Japanese believe they've improved on colour, stability, and luster is because the published values for jet say it can be black and brown, it has a dull, earthy, or resinous luster, and a very poor stability. Now, true jets are jet black, have a mirror-like luster, and exceptional stability in the archaeological record. That's why we see jet items that are 26,000 years old in Europe. So really, this is not an improvement, and the fact that the gem notes are so wrong allows these claims to be made. Just going to leave you now with when I speak to Native American workers. So Native American Indians have worked jet for millennia probably. They tend to use jet as the night sky. And when I asked this Navajo worker, why does he use jet? Why is it significant to the Navajo? He said, well, that's easy. Without jet in the world, there simply would be no color. We need jet as the background to the color in our life. And I really liked that analogy. So hopefully I haven't overrun. Thank you very much for listening. There's my contact details, and I put lots of my research on Instagram if you're on Instagram.
Wow. And you didn't take a breath.
No, I didn't, did I? No.
That is utterly amazing. Thank you so much.
You're
That
welcome.
was almost more than I could absorb, but I've just kept me on the edge the whole time. Thank you very much. That was most interesting, and you are a walking encyclopedia. I am so glad we got you.
Thank
So if
you.
you can hold off till we're finished, I know that that's a little bit of a patience thing that I'm not good at, but I'm hoping people will have put some good questions forward because that was a very interesting talk about something I know so little about. So thank you for educating us. I really appreciate it. So now we move on to our second presenter. And thank you once again, Sarah. We'll look forward to answering questions at the end.
Okay.
So just for the record, Rosie Young is a rather interesting lady. She's a gemologist at the GCS lab in London. She started studying her gemological BSc at Birmingham City University, and she did a final major project on sunstone there, and completed a research internship also about sunstone at GIA in Carlsbad. So she's got all the creds anyone could ever want. And this year, of course, she passed her FGA, which I unfortunately never did. So I'm jealous. Anyway, I'd like to welcome Rosie to our ranks and ask Rosie to share with us something of the gemology of sunstone. I'm very interested to hear about this. And please keep your eyes and ears open. So if you have some questions at the end, we can help learn from your questions as well as from what Rosie has to say to us. So Rosie, can you when you're ready, go for it.
Brilliant. Yeah, thanks so much, Ray. And thank you, Sarah, as well. It was really interesting listening to your talk and learning a bit more about Jet. So for my portion of the evening, I'm going to be talking about sunstones, which is my area of personal interest in gemology. Yeah, as per your introduction, yeah, I've done a couple of research projects on sunstone of my own, and yeah, now I'm a gemologist at GCS Lab in London. I've been there nearly 2 years, and in that time, I've had exactly one sunstone come into the lab. So I'm always hopeful that we're going to get more, but sadly, yeah, it's not a very common thing. Um, but yeah, so let's start off with defining sunstones. So what is a sunstone? So first off, sunstone is a feldspar. It doesn't have to be a particular feldspar composition. So in a lot of notes about gemstones, it will say, oh, sunstone is a liga-glazed feldspar, but not necessarily. As we'll see sort of over the course of this talk, there's quite a bit of variety in sunstone. To be a sunstone, it must have some kind of phenomenal inclusions to give it an eventurescent effect. And then we also have meanstones. So meanstone features an adulorescence or a Schiller instead of eventurescence. But the two effects aren't mutually exclusive. So we can have one gemstone that's both a sunstone and a meanstone at the same time. So going into feldspars, just to do a bit of a refresher on the feldspar sort of group of minerals. So feldspars are the most abundant minerals in the Earth's crust. So we're probably all sitting above some feldspar right now. But I feel like we don't actually talk about them that much in gemology because good, like large gem quality crystals are reasonably rare, despite the abundance of feldspars in general. So if we look at the ternary diagram, we've got three sort of different end members that we're looking at. We've got orthoclase, which is the potassium feldspar at the top. We then have albite, which is the sodium feldspar, and this is just a simple substitution of potassium for sodium in the chemical formula. So this is the alkali feldspar series. We then have plagioclase feldspars, and this gets a little bit more complicated because we're substituting sodium for calcium towards the end member of northite, but the formula is different between the two. So we also go from having one aluminium atom to two aluminium atoms, and from having three silicon atoms to only two silicon atoms. And the plagioclase series is divided into different categories. These are reasonably arbitrary, just based on the percentage of a northite present. But so we have, for example, a ligoclase, andesine, labradorite, bitownite. A northite itself is extremely rare. It's very unlikely to get a crystal with that high of a calcium content, but it is extremely common on the moon. So you will have seen some, just not where you might expect. And then the white area of the ternary diagram here is the miscibility gap, where we don't have any feldspar varieties. So if that wasn't complicated, this is where it gets more complicated. So feldspars, they can be monoclinic. Most of them are triclinic. The variety we get is dependent upon the temperature at which the crystals form. So in the potassium feldspars, with exactly the same chemical composition, we might have microcline, sanidine, or orthoclase. Often crystals are zoned. The chemical composition of the melt might change as the crystal is growing. So we might have different feldspars in the same sample for that reason. There's also barium feldspars, not shown on the diagram here. So this goes to the end number there is called Celsian, and it's a series between potassium and barium. And this means we can get some quite complicated combinations. So, for example, a plagioclase feldspar might contain, say, up to 5% potassium. It might have some barium in there as well. It's not always clear cut. And then the other thing that's important to what we're talking about tonight is intergrowth. So where the composition of the melt when the crystals are forming is kind of within the miscibility gap, what happens is different feldspars will form in intergrown layers. So you might have something, for example, that's mostly orthoclase with some thin layers of albite growing in between. And this is particularly interesting because this gives us some of the phenomenal effects that we might see in feldspars. So if you look at the diagram here, the areas that look like kind of curvy ladders, this is where we're getting intergrowth, which is relevant to us as gemologists. So we have a geolurescence in moonstone is the top one. So this is a material called adularia. We also have in the bottom corner peristerescence, which is also moonstone, but it's a moonstone of a different composition. We have labradorescence in the middle. So I think we're all familiar with labradorite. And then we also have, you can have the intergrowth of like higher calcium feldspars, but this doesn't cause any phenomenal effects. It's just simply different layers. As well, if you see something like a sample of a amazonite, you may well see sort of like a streaky appearance to it, and this will be intergrowth of different layers as well, just not causing a phenomenal effect. So if we have a piece of feldspar, how are we going to determine the chemical composition of it? So all of these different feldspars in their pure form are colorless, but they may show color because either of impurities, trace elements, or different phenomenal effects, as we're seeing in the sunstones. So ideally, to determine the feldspar composition, we do some kind of chemical analysis, for example, with LAICPMS. But this equipment obviously isn't always available to us. So the best way to do this with basic testing is to just take the RI and the SG. So the refractive index increases between orthoclase and albite, and increases again between albite and anorthite. So as you can see in the table on this slide, there is quite a big difference. Like the RI is substantially higher for anorthite versus orthoclase. So this can give you a reasonably good estimation of what your feldspar composition is. The problem really with sunstones is they're often cut as cabochons. So you might not be able to get a really good RI, but you can hopefully get a distant vision, which will give you a bit of an idea. The SG also changes with feldspar composition. The problem here with sunstones is that to be a sunstone, it's going to be very heavily included. So the inclusions obviously have their own mass, and that's going to influence the SG. So the SG may not always give you the most accurate result, but it should be helpful in helping you determine, are you looking at a plagioclase or orthoclase here? So moving towards advanced testing, Raman analysis won't be able to give you the exact feldspar composition, but it is very useful for telling you whether you have orthoclase or plagioclase. So there's a shift in the major Raman peak, which we can see in the graph here, which has two samples from the rough database. But the exact position of the peak isn't going to give you the exact composition. It's just a case of if it's above a certain value, it will be orthoclase, and if it's below, it'll be plagioclase. So when I started becoming interested in sunstones, I was kind of looking for a guide that would set out all the different types and tell me a bit more about them. I still haven't really found this, so I've kind of just come up with my own categories. So this is how I categorize sunstones. As you'll see as we go through, it can get a little bit messy at times, as a lot of stuff does with feldspars. But yeah, so these are the categories that I use. So metallic sunstones, which have platelets of copper. So I'll go over these quickly this evening, but I'll be focusing more on the other categories. We have confetti sunstones, and these have randomly oriented hematite platelets. We have lattice sunstones, which are my personal favorite, and the inclusions form a geometric pattern. And then I've also just done a miscellaneous category, which is everything else that might be referred to as sunstone, including a bunch of things that aren't sunstone, but might well get mistaken for it. So first off are metallic sunstones. So this is most famously Oregon sunstone. You can also find metallic sunstones in Ethiopia and the Ethiopian material is really quite similar to Oregon sunstone. And Mexico, the Mexican material doesn't have the same color, but it may have some copper platelets. So the copper platelets that are eye visible and give this sort of beautiful, like shimmery, glittery appearance to the sunstone, these are known as schiller. And you also get some like nanoparticles of copper in different sort of shapes and sizes, which cause color. And so the copper can cause red or it can cause green. As you can see in some of the pictures here of some larger rough crystals. And then here on this slide, just a few more examples of some Oregon sunstones where you can see the sort of like the distribution of the color and of the copper schiller as well. So Oregon sunstone, it's plagioclase. Usually it's labradorite in composition. I think some of the Ethiopian sunstone has been analysed and found to be bytonite, which is like the next one over towards the calcium end. So labradorite, it doesn't have to show labradorescence because it doesn't necessarily have the different intergrain layers of feldspar. So yeah, it simply means that this is a crystal with that particular composition of plagioclase. One very cool thing is that the green areas in Oregon sunstone are very highly pleochroic. So at the bottom of the screen, we've got a cabochon where you're looking at it face up, it's green, but turned from the side, the same area looks red. And one very cool thing is that if you're able to cut a stone like in between the two, you can sometimes get a dark purple color, which also can make a very attractive stone. So here's a photomicrograph, which I took of some crystal inclusions in an Oregon sunstone. So you can see in the background the sort of diagonal stripes. This is where all the copper schiller is. It often forms in this kind of banded formation. And then in the tension fracture around the crystal, we also have some metallic copper as well, which you can sort of see is giving this like reflective areas. Olivine crystals are reasonably common as an inclusion in Oregon sunstone. I mean, this is material that's coming up in lava, so it's basaltic, so it makes sense to be finding olivine here. And here's the same crystals from another angle where you can sort of see the copper schiller surrounding them in the sort of areas of stress in the crystal. So Oregon sunstone is often imitated by diffusion treatment. So the way this works is that people will take colorless feldspar crystals. So it could be labradorite, like Oregon sunstone. Most commonly it's andesine, which is a lower calcium plagioclase. But it doesn't matter too much what the composition is, because it seems to work with different compositions of plagioclase. But essentially, yeah, it's natural crystals. They're put in a furnace with some kind of powder mix, including powdered copper. And then even within a day or two of heating, this is enough time for the copper to diffuse into the feldspar and create something that can sometimes be really quite a convincing alternative for Oregon sunstone. There's a whole bunch of different methods for telling the difference and kind of quite a lot of history here from when this first hit the market. I'll just give you a quick method that I like to use, which often works, is looking at the color zoning. So in natural Oregon sunstone, you'll often get this watermelon type coloration with a red center and green around the edge. And this isn't always the case. You might have just red, you might have just green. But what I've never seen in natural Oregon sunstone is what's at the bottom on this slide, which is reverse watermelon, the green on the inside and the red on the outside. So if you have a piece, I would ask yourself the question, if it was a watermelon, would I want to eat it? And if the answer is no, then it may well be diffusion treated. So moving on to the confetti sunstones. So this category of sunstones, so they're found all over the world. Most commonly, I would say in India, Tanzania. You can also get Russia, Norway, Malawi, Madagascar, quite a few other places. So these sunstones have hematite platelets, which will appear like red or orange, and they'll reflect rainbow iridescent colors. So usually this kind of feldspar is oligoclase, um, but it is variable. And often the kind of sunstones you'll see, like they'll look orange, and that's literally just because there's so much orange hematite in there. It's giving an orange appearance overall to the stone. My personal favorite of these is the two at the bottom, like the pale green sunstones. These are found in Tanzania, um, and they sort of have patches of hematite, but then with areas of higher clarity where you can see this lovely like pale green feldspar. But yeah, these are reasonably hard to find. Some other inclusions you might see in the green material, they have quite a lot of colorless needles, which I did some micro ramming on some of those and found them to be some anthophylites. Sometimes you can get other minerals in there, like I think there's some epidate in the cabochon on the right. And then here's another nice picture of some of the hematite platelets when they're catching the light and showing all their iridescent colors. So hematite is hexagonal. So when you're seeing these platelets, they will generally be hexagons. Some of them might be quite distorted. They might be like pseudo hexagonal, like maybe the hexagon is kind of stretched out, the sides aren't all the same length. But for the most part, you should be seeing mostly hexagonal shapes when you're looking at your sunstone on the microscope. This material, purple haze sunstone, is got quite popular recently online. I don't have any of this one myself. From the pictures I've seen, I'm not sure it actually looks particularly purple, but I think in these pictures you can see maybe like a hint of like a purple sheen to it, which is quite attractive. But this kind of thing would fall under the banner of the confetti sunstones. Russian sunstone is quite unusual. So this one isn't a oligoclase, it's actually a potassium feldspar, and the composition falls into anorthoclase. So this is quite unusual. So it's a different composition to most of the similar looking sunstones. The feldspar itself is quite a dark brown, so it has a distinctive look. And it also has like a white moonstone flash. So if it catches the light just right, you get a bit of a moonstone effect. So it's doubly phenomenal. Which yeah is quite interesting. Also in the middle picture, you can see some little triangle inclusions, and these are magnetite as well as hematite. So moving on to the lattice sunstones. So what makes a lattice sunstone? So a lattice sunstone, so it's orthoclase feldspar, so these are the potassium feldspars, and they have inclusions of hematite and magnetite. So they're most famously found in Australia, a material called rainbow lattice sunstone. But you can also get lattice sunstones in Tanzania and a few other localities as well, which I'll go over here, the ones that I'm aware of, but there may well be more out there. So to think of like how the inclusions are working here, if you imagine like a book with transparent pages and different inclusions being printed on different pages of the book, if you were staring down, like you're looking at all the inclusions, but they're on different layers within the mineral. And a key thing with the lattice sunstones is that the inclusions are crystallographically oriented. So in the Australian material, we have these like elongated, like blade-like inclusions, and they always intersect at a 60-degree angle. And it very much like the inclusions are growing sort of or exolving like in the feldspar, and they're very much bound by the structure of it. And if you look in the picture at the bottom of the slide in the middle, you'll see these lovely equilateral triangles, which are quite a common feature of rainbow lattice sunstone. And you can see in the picture the triangles are either pointing upwards or they're pointing downwards. Again, like they can't go at different angles. They're very much bound by the crystal structure. There is a bit of variety, like some of the Tanzanian material, it's more of like a parallel lines rather than intersecting blades. And just to complicate things, you can also get the confetti type inclusions in lattice sunstones. So if you look at the sample, at the bottom corner of this screen, this is one that I have myself. And the right half of the sample is very clearly a lattice sunstone. And then the left part is just randomly oriented hematite, confetti type inclusions. So you can actually quite often will get both at the same time. So yeah, here's a nice example of some Australian rainbow lattice where again we can see the equilateral triangles. So key points for lattice sunstones. They also have magnetite, not just hematite, like we were saying before. And the platelets are not growing in random directions. So the Australian material, it's found in the Northern Territory. It's quite a remote location. I think it's in the zircon fields. And the Tanzanian material, I think there's a lot of different sunstone deposits around Tanzania, and there's a lot of different types of sunstones coming out of there. I have been advised that some of it comes from the south of Tanzania near the Mozambique border, but I haven't had that definitely confirmed. And I imagine there's quite a few other deposits around Tanzania as well. So it's hard to sort of nail that down to a clear answer about where the mines are. There have been some lattice sunstone found in the US, in South Carolina, but I think there's only been a few pieces ever found, and it's never become commercially available. So yeah, here's a nice example of having both the kind of rainbow confetti hematite platelets with the lattice inclusions as well in an Australian sunstone. So in this picture, we've got 3 different types of inclusion that are making this feldspar into a sunstone. So first of all, we have magnesite. So this is forming the equilateral triangles and the geometric lattice. And you can recognize the magnesite because it's black, it's opaque, and it's got a metallic sheen and reflected light. Now, some of this magnesite has then oxidized to become hematite. So magnetite is a cubic mineral, Fe3O4, and hematite, as I mentioned before, is hexagonal, and that's Fe2O3. So as the ratio of oxygen to iron is increasing, it's weathering into hematites. And we can recognize the hematite because it's brown, it's translucent, and it will give rainbow iridescent colors in reflected light. So the key thing here is that where we have the hematite in this form, it's in the shape that was already determined by the magnesite, which is of a different crystal system. And then we also have some hematite, which is just formed as hematite in the first place. So this is hematite in the normal hexagonal confetti kind of form. So if I show you this image, if you have a look at some of the parts which are brown and some of the parts which are black, then I'll show you it with different lighting and you can see the difference. So here, as you can see, the areas on the picture before that were black now appear kind of grey metallic. And then the areas which were brown, we now have these lovely rainbow iridescent colours that give rainbow lattice its name. I'll just go back again so you can kind of see the comparison. And then, yeah, here's another nice example where you can see some of the hematite and some of the magnetite. This was a nice sample that I was lucky to be able to photograph. So in this case, I initially wondered if there was some kind of banded structure in the sunstone, but what appears to be happening is there's maybe some kind of very fine particulate in the sunstone. And as light is reflecting off the hematite, it's actually giving this kind of appearance of rays, kind of like, if you shine headlights in fog, that kind of effect. And so there's a better picture here where you can see the effect there, which I think is quite interesting. If you look at the top right-hand corner of the screen, you can kind of see one of the small hematite platelets with a ray coming off it to kind of give an idea of how the effect is created. Another inclusion you might find in this kind of material is mica. This was a cabochon I bought for myself. It was a lovely pear shape, and then I dropped it and the top of it cleaved off. But it did show me this quite substantial mica inclusion, so that was kind of the silver lining there. You can get a kind of lattice sunstone in Sri Lanka. I've seen one example of it, which I've got some pictures of here. It's not quite the same kind of lattice pattern, but I think it's very much the same kind of inclusion that we're getting. Same for Burma. This was something that was labelled as a Burmese moonstone, but again we can see we've got some kind of lattice lines and again the equilateral triangle kind of inclusions. This was a very unusual sample which I came across completely by chance, which I've called 90-degree lattice. So in a normal lattice sunstone, we have an intersection angle of 60 degrees. In this stone, the angle I'm getting is closer to 90 degrees. And it also just appears to be hematite. I didn't see any magnetite in this sample. This one is plagioclase rather than orthoclase, and I think maybe the different feldspar structure has led to a different pattern appearing. But to be honest, I have no idea why there is a lattice pattern in this sample, but I thought it was quite cool. So hang on, here's a better picture for you. So as you can see, there's quite a lot of these kind of like elongated platelets that are all intersecting at the same angle. So the Tanzanian lattice sunstones, these are reasonably new to the market. There's three types that you might commonly come across. And the first is where the feldspar is quite like grey, brown, smoky, and the inclusions of the hematite and magnetite are in parallel lines. Like a good quality example of this might be called meteor shower sunstone. It's quite a common term. There's also similar material, which is like a rich, like orange, yellow, gold kind of colour. And then the one in the bottom right, which I've just called full lattice. This one best imitates the Australian rainbow lattice sunstones, and it does have a very similar pattern to it. And so here's an example of some of the Tanzanian material. You can see this like bright white equilateral triangle on the screen. So we're getting like a very much the same kind of shape to the inclusions in some regards. Some of the other inclusions, they're sort of like a more irregular shape. We do have some intersecting lattice lines, but they're much thinner and finer, which is quite different to what we're seeing in the Australian material. Here's another example. Here you've got a lot of kind of parallel lines with some finer intersecting lattice lines as well. So some of the Tanzanian material can be a reasonably convincing alternative to Australian. And I actually think I've bought some before being told it was Australian before I knew the Tanzanian stuff exists. So you definitely can be fooled by it, as I was. So here's some examples of the Tanzanian material again. So to do a comparison of how would you know the difference if you're buying a sample of this for your collection. So the top two pictures are Australian and the bottom three are Tanzanian. So the Tanzanian has a kind of smokier, hazier appearance to the feldspar. The inclusions will show like a more ragged edge, whereas the Australian is more of like a crisp, straight edge. Likewise, the Australian inclusions look smoother, whereas there's more of like a crepe paper kind of texture in the Tanzanian samples. And the Tanzanian also have these kind of thin, fine lattice lines, which isn't something that I've yet seen in Australian samples. Both can have moonstone effects, so you might well get a white moonstone flash if you angle your sample just right, due to the intergrowth of different feldspars in this kind of material. There is a trade name of eclipsite that's been trademarked for some of the Australian sunstones that do show this effect of sun and moon all at once, so quite appropriate. So in terms of chemical analysis and telling the difference between the two, their published data gives quite wildly different results. So there's an article in the European Journal of Mineralogy that gives the Australian material as having 83% orthoclase. There's one in the Journal of Gemology giving 96%, and on the Rainbow Lattice website it gives 75%. So there's a bit of a range. From samples that I tested from my own collection, I found the Australian has a range of 82.66 to 85.34% orthoclase. and then Tanzanian between 71.85 and 81.07. So there wasn't any crossover in the chemistry between the two, but as the ranges are pretty close together, and I didn't do a huge number of samples, it is possible that there might be a little bit of crossover, but this could still be a useful method for separation. And likewise, some of the trace element chemistry was a little bit different as well. A couple more examples here. So this could be another method for separation. So miscellaneous. So this is now just going to be everything sunstone or sunstone adjacent that hasn't fit into my previous categories. So we have, first of all, on the left, this lovely aventurescent Sri Lankan orthoclase, which is full of thin films, which gives a nice phenomenal effect, even though it doesn't really fit into any sunstone category. A lot of material is sold as sunstone, but doesn't have any phenomenal inclusions. So the pictures are of some yellow feldspar from a place in Utah. Also, a lot of the material found at the Oregon sunstone mines is just kind of pale yellow without any of the copper inclusions. Another bit of a grey area is you might have, for example, something from an Oregon sunstone mine, which is red, so it's coloured by copper, but it doesn't actually have any visible copper platelets. So it's not technically phenomenal, but that might well be still sold as a sunstone. A question I got asked after doing a previous talk was if you have a piece of labradorite, as in the classic kind that shows labradorescence, and it has a bit of a glittery appearance, what's this? Is this sunstone? Is it hematite? And so I had a look at some of mine, and in this case, these inclusions are ilmenite rather than hematite. So they're kind of little black needles with a metallic luster, but they can give a bit of a sparkly effect if they're quite abundant. So you could kind of argue that this is also a sunstone, but I think that this effect is very much overshadowed by the labradorescence. So I don't know if anyone would actually categorize it that way. Another material that I sort of started to notice last year is this stuff called Malawi moonstone. I have heard reports that it's actually from Tanzania, so I don't know if it is Malawian or not. I like to call it Rainbow Road sunstone because I think it does have a bit of a sunstone effect to it, and Rainbow Road for obvious reasons. But yeah, so this is a transparent, colorless material, and when you catch the light in it just right, you get these beautiful kind of iridescent rainbow laths going across it. As there's not anything published about this that I've seen as of yet, I did a little bit of testing myself just to get an idea of what feldspar composition it was. So first of all, doing the Raman analysis, it's got a major Raman peak at 509, which suggests that it's a plagioclase rather than orthoclase. And then doing the RI and the SG. So I didn't have any with a perfectly flat polished surface, so I just did some distant vision RIs, which gave me like 1.53 to 1.54. So if you look at the horizontal rainbow arrow on the chart, that kind of shows we're in the range for like elbite or a ligoclase, so like a low calcium plagioclase. The SG was quite variable and didn't give me a very reliable answer, but all the readings I got were in the range for plagioclase. So again, it's suggesting that this isn't an orthoclase feldspar. And then I also did some testing with an XRF gun. So unfortunately, this doesn't allow me to detect the amount of sodium, so I can't get a percentage for what feldspar composition this is. But it does let me get a good idea of where it's sitting, because I can measure the calcium and I can measure the potassium as well. So if we think about the plagioclase series, as we're going from albite to a northite, we're going to have more calcium. And then, as I mentioned earlier, we're also going to have more aluminium, and we're going to have less silicon, as there's 3 changes in the chemical formula over this series. So I took a reading for some Oregon sunstone, which I know is labradorite in composition. And the values are in the table there, and we can see that this Rainbow Road material, it has much less calcium, has much less aluminium, and it has a bit more silicon, a bit more potassium as well. which is to be expected. Obviously, feldspars are often quite mixed. So this is suggesting to me that it is a plagiate clays, but it's much more towards the albite or oligoclase end of the diagram. So beyond sunstones, what else do we have that might kind of get mistaken for them? So other eventurescent materials. Obviously, we have aventurine quartz, easy to distinguish because it's coloured by green mica rather than hematite or the other inclusions we've been looking at. Goldstone is a common simulant, so this is just glass with some octahedral copper crystals within. Another good one is bloodshot iolite, which is a very horrible name for a very nice gem. And this basically has exactly the same hematite confetti inclusions that you would see in a sunstone. It's just in cordurite instead of feldspar. And even more confusingly, this can actually integrate with sunstone. If you look at the cabochon in the middle at the bottom of the slide, this is a picture that I took from a microworld article in Gems and Gemology of iolite and sunstone growing together, both with the same kind of inclusions in, which is pretty cool. And then another thing which I was sold sunstone but isn't is this rough material that I bought as Norwegian sunstone. And a friend of mine very kindly offered to cut it into some cabochons, but as he started cutting it, realized it was much harder than expected, with a hardness of like as you'd expect of quartz rather than as you'd expect from feldspar. But it did have some areas which were showing these iridescent reflective platelets. So I was still kind of hopeful that maybe, you know, at least some of it is sunstone. But sadly not. So doing some comparisons with some spectra from the rough database, turns out that the areas with the iridescent platelets were actually cordurite. So these were kind of, although colorless, it was essentially the same as a bloodshot iolite in patches. There was also some quartz, a bunch of other minerals. We had some zircon, some rutile, some sillimanite, but absolutely no feldspar. So yeah, sadly, it was not technically a sunstone. Okay, well, that's all from me. Thank you everyone for listening and happy to take any questions.
All right, so since you're at the end, I'm going to ask any brave souls amongst us to, if you have a verbal question, now is the time to ask Rosie. I have one though. I have a beautifully cut blood red Oregon sunstone, which is eye clean. Is it, by your definition of sunstone, if it doesn't show any of the effects that would be consistent with inclusions such as you've just been demonstrating?
Yeah, I think it's always difficult with that kind of material. I think personally, like if it has color, I still like to call it a sunstone, even though you could say technically it's not because it doesn't have any phenomenal inclusion. So I definitely think it's a gray area, but I also wouldn't know what to call that kind of material other than sunstone, because obviously it's still, you know, like very nice, valuable gem quality material that can still make, you know, like very beautiful jewelry. So it seems a shame not to call it sunstone still in my book.
Thank you. Thank you very much for all the work you put into this, and obviously you've got a broad knowledge, which is actually quite interesting to hear, talking about someone in the gem world talking about all the different phases of feldspar is not a common thing you're going to hear. So good for you. Clemens, can you take a look on the chat and see if we can pull some questions for both these ladies? And maybe we could have a split screen so both of you could be on.
Oh,
I
that's
don't know if that's possible or not, but
I can at least try to have all the people on, so that would work from my side. I don't know what you see, but I just go on with the questions, and we start with the questions from the chat side. What is the difference between mineralized and jetonized, Sarah?
Well, the jetonized material doesn't really show any mineral structure. It is possible to have areas of crystallization in coals, but essentially, you know, it's an organic material, so you're not seeing crystal structure. We do see crystal structure in the mineralized sections, so it might be quartz, it can be carbonate minerals in there as well, but we don't see that obviously in the jetonized material.
Yeah, I think that also answers the next question. Has jet been tested by Raman?
There was a trial many years ago, and I've suggested it's people that have Ramon, and they've been like, it's combustible. I'm not going to put it in my machine. But I don't have access to Ramon, and it's my understanding that it's better suited to crystalline materials, whereas obviously FTIR is better for organics. So because FTIR gives me good results, I don't feel I necessarily need Ramon. The only thing I would potentially be interested in is I think that there are some inclusions in jet. I think we might have some oil-filled structures within the jet. So it maybe would be good if we could maybe use, some sort of micro probe to look at those structures. But yeah, if somebody wants to do some Raman on it, then, that's something we could definitely look at.
Send me some samples and we will do this.
Yeah,
From a practical point of view, I can tell you it's for both for FDIR as well as for Raman, black material is the worst thing that you can have because it absorbs
yeah,
all the energy.
yeah,
And as you said, Raman is much better for crystalline materials. Uh,
yeah.
you have the non-polarizable bonds. You might see a couple nice things if there is enough wood still inside.
Hmm.
But typically, you burn your material when shooting with a laser.
Yeah,
FDIR is by far the better choice.
yeah.
So, what else do we have here? How many varieties of jet are there?
Well, I'm going to tentatively say there is possibly up to 6 in the Whitby area, and I see most of them elsewhere as well. Whether all the varieties are true jets, because the brittle material looks much more like a vitrinite-rich maceral, which is the texture is more similar to what we'd see in normal humic coals. The thing with jet is it's highly impregnated with oil and therefore is really high in hydrogen. And usually, as we increase ranks or metamorphic grade in coals, the volatiles are driven off. We don't see that in jets. So, for some reason, this hydrogen impregnation really stops the normal coal progression at the point of more or less of um, diagenesis when it's first buried in the sedimentary sequence. So it may be that some woods in the Whitby area have not received that oil impregnation and they've gone on to develop traditionally. So when I read the papers about the Turkish material having jets and lignites in the same strata, it may be that some of the materials that traditionally we call jet in the Whitby area are not true jets. But we definitely have hard, soft, cord, and brittle jets at every locality I've been to globally. Then we have these uniquely Turkish ones. We have pyritized jets in Spain. The sulfur in Whitby jet is organic, so it simply can't bond with iron and make pyrite. That's not the case in the Asturian jets. Some of the Spanish jets are heavily pyritized. So there may be, and some of these groups, these varieties are probably end members as well. So we have intermediate materials as well. It's quite a complex picture at the minute. And I'm not doing any thin section work, so because I need my testing to be non-destructive. So really we'd need to do petrographic studies to really get to the bottom of it. And I'm just haven't got time to do that at the minute.
So one more question. How does jet relate to the Russian shungite?
Well, shungite is a really interesting material, and I wrote an article for GemA on shungite, but shungite is Precambrian, so it's about 2 billion years old. It was believed initially to be elemental carbon, but I think it's now proven that it's organic in origin. And pure shungite, silver shungite, is above 98% pure carbon, so it's a mineraloid and it has really quite astonishing antioxidant properties. It has the Buckminster fullerene allotrope of carbon in it, so it can be used for water purification. I believe it's a superconductor. Jet doesn't conduct electricity at all, which causes me problems. But yeah, quite an amazing material, but not really related to jet other than it is organic carbon in origin.
Okay, so thank you. Are there any live questions for Sarah that we want to have?
I actually had one question. When I first started cutting, I played with anthracite and I actually got a very high polish on it.
Yeah.
And I'm wondering if anthracite is ever used as an imitant.
Well, certainly in areas that have really good quality anthracites, and I think in Philadelphia there's a craft centre around anthracite historically. We certainly see Welsh coal carvings in anthracite. And actually, a couple of years ago at the Greenwich Naval College in London, there was an art exhibition called Coalescence, and the artist used 2.5 tons of anthracite to make a phenomenal type of display showing the luster, the metallic luster of incredibly high grade coals. And that was really quite amazing. So certainly anthracite is an incredibly decorative material. It has a luster more similar to graphite. You know, we're
Yeah.
almost at the limit of carbon being stable at an anthracite level. But yeah, it is absolutely carvable. And I think that a lot of the Chinese jet on the market and even the Australian jet on the market is an anthracite because it does have a metallic luster to my eye. We don't know the exact localities, unfortunately, of those materials. They just appear at Tucson and are retailed as Chinese jet. But yeah, definitely other
I
coals
actually,
can be.
I was very fascinated to hear about your experience with the Turkish lady jet carver because
Mm,
it reminded me of someone trying to teach me to be a better onophile. And by checking the different scents and flavors and coming off. And so clearly olfactory is a big part of, although it doesn't sound scientific, it certainly sounds
mm.
very effective as a means of determining.
Yeah, I think even as a lapidary, you know, anybody who cuts stones know we are using sound a lot. Certainly, you know, we detect flaws in jet from the sound on the wheel, you know, on the lap, diamond lap. So often we can hear a problem before we see it. So yeah, we are using other senses a lot in Blackstone, I think. And that's missing from gemology to a certain degree. Um, so yeah, certainly they are important considerations.
Well, both you ladies have given us a great tease for what you might be doing at GEMA. So thank you for sharing yourselves and your time and your knowledge with all of us. And I do hope you have a great year ahead of you. And we really appreciate your donating your time and energy to help educate the people that watch our Gemquest programming. And if you don't mind, it's going to be available for people to look at for years afterwards. So I'm sorry, Jim A.
No, no, it's our pleasure. I'm sure Rosie would agree.
Okay,
Yeah,
well,
absolutely. Yeah. Thanks for the invite. It was really nice to do this.
Mm.
well,
Can
I
I
hope you guys had fun
Sorry, I was just
doing
going to
this.
say one last final request, and I noticed somebody in the chat had mentioned Colorado Springs. I desperately need a specimen of jet, and it is Colorado Springs near Denver. So I don't have a Denver specimen, and I don't have any Utah jet base in Utah samples. So on the off chance anybody sees this and knows localities for those samples, I would very much appreciate a sample
Well,
for the sample suite.
I'm going to be in Denver, and I will ask at the museum there because if anybody's going to know, I would suspect that they would have a lead for you. And if I can find one, I'll send it back to you and let you know. Maybe
Thank
even be able to get a sample. Who knows?
mm,
Okay,
So,
I have one question for Rosie. You
Yeah.
show nice diffusion of the copper with these watermelon and inversed watermelon. Do you have any idea why these inversed watermelons will form?
Um, no, I don't. It is something I would love to figure out. Because you can definitely get a lot of the diffusion treated stuff which forms similar patterns to the natural. where you might just have like a red center and a colorless rim, which is very common in both. But yeah, I wish I had an explanation for why you get the reverse watermelon, but I don't. Apparently, the difference in the red and the green is to do with the size and the shape of the nanoparticles of copper. So it must be I don't know, form preferentially in a different way. With the diffusion treatment, maybe as it happens faster, this affects it. But yeah, I wish I had a good answer for you, but I don't.
But it's not something that's really simple and obvious, like the concentration of the copper would be different.
Yeah, it is usually a higher concentration of copper in diffusion treated samples, but I don't know whether that is making a difference or not in terms of the distribution of the color.
Yeah, for a chemist, it's always the problem if you're inhomogeneous material. Yeah.
Yeah.
Just one spot and the next spot, and all the readings are completely off.
Yeah.
Okay, any more
Well,
questions for Rosie? Ray, you had a couple of comments on the Sunstones.
well, I only put out there that I'd like to get a really good sample of the lattice because I've seen pictures online. I'm thinking, oh my goodness, that is amazing looking material, especially when it's so rainbowy sometimes. I mean, it isn't always, but when it is, it's amazing. So I've been looking for a while for a good lattice specimen. So I'm told that in response that there might be a booth at Tucson. So I'll keep an eye out.
Yeah, there is. Yeah, I visited this year. So it's basically one mining claim where the Australian material is mined, and the guy who runs it does do a stand in Tucson. So if you get the chance, you can go have a chat to him and see some of the stuff that they're mining. But yeah, that would probably be the best place to get it.
Thank you so much, everybody, and hope you have a great day. That's what's left of it, and I really appreciate you giving us your time, and I hope that you have a great time doing it again at Gem A.
Thank you.
Okay, ladies, thank you so much. Thank you, Clemens. Thank you, audience, and we'll look forward to seeing you at the end of August. Okay.